Hi, this is Dr. Anthony Revis with SVSU General Chemistry 111, Lecture 2 of Chapter 2, Atoms, Molecules, and Ions. The following topics will be covered, but not necessarily in this order. We'll take a look at early ideas of atomic theory, evolution of atomic theory, atomic structure and symbolism, that is, the symbols used, chemical formulas, the periodic table, molecular and ionic compounds, and chemical nomenclature. When we consider atoms and molecules and ions, and we look at the states of matter, we recognize that matter is composed of molecules composed of atoms. In other words, atoms are the building block of molecules, and those molecules are the building blocks of matter. When we look at the subatomic particles, we note that they're composed of protons, neutrons, and electrons, and the protons and neutrons make up the nucleus of the atom. Shown here is an example of lithium, which has an atomic number of 3 and has a mass number of 7. Therefore, it's composed of 3 protons and 4 neutrons. But this is an example of what atoms look like. Atoms are composed of a nucleus, which contains the protons and neutrons, and is surrounded by electrons. Now, because mass is such an important feature in an atom, one of the ways that scientists measure, monitor, or assess the progression of atoms toward molecules as matter is by examining the atom's atomic mass. So let's take a look at atomic mass. Let's talk about the concept of atomic mass. Now, atomic mass will be referred to as, obviously, atomic mass, but is also referred to as atomic mass unit. Okay, so keep that in mind. You'll hear the terms interchange. You'll hear atomic mass, you'll hear atomic mass unit. Atomic mass unit is the value assigned to the atomic mass. So let's talk about it. So what is atomic mass? Atomic mass, or atomic mass unit, AMU, is defined as precisely 1/12 the mass of an atom of carbon, that is carbon-12. Okay, so essentially carbon-12 is the standard by which atomic mass units are assigned. Carbon-12 atom has 6 protons and 6 neutrons in its nucleus. Therefore, it has a mass number of 12. There it is, why we call it carbon-12. Okay? But the 12 is not its atomic mass. Neither is it its atomic mass unit. Okay? Keep that in mind. It'll become clearer as we go. All right? And AMU is the average of the proton rest mass and neutron rest mass, and is approximately 1.67377 times 10 to the minus 24 grams. So if you have that number of grams, that's what the mass of a proton or a neutron at rest would be. And so it's extremely, extremely small. Now, the mass of an atom in AMU is approximately equal to the sum of the number of protons and the neutrons in the nucleus. It is not the same, but it is an approximation. Therefore, in discussions about subatomic particles and atomic mass, you must differentiate between its mass number and its atomic mass unit. Okay? Even though it's an approximation, it is not the same as the mass number. Mass numbers are whole numbers. Atomic mass units will contain a decimal. That's one way to simply look at it and be able to identify it. So if you look at the value and it has a decimal, that's an atomic mass unit. If it does not have a decimal, that's a mass number. We show you here the values for the mass of the protons and the electrons. here. And we also show you what the particle atomic mass would be. In other words, a proton and a neutron both have approximately 1 AMU as the atomic mass or the atomic mass unit for its particle. That is different from its at-rest mass of approximately 1.7 times 10 to the minus 24. Keep in mind, depending on whose textbook you use or what literature, you will see some variations in the mass reporting of the at-rest mass. Don't let that bother you, okay? Let's repeat. Atomic mass or atomic mass unit is defined as 1/12 the mass of an atom of carbon. And what's very important to remember about that is it is an average of the proton and average of the neutron. That's what an AMU is. So what are some outputs from understanding what an AMU is or atomic mass is? Okay, ready? These points are worth remembering. The atomic mass of an element is the mass of an atom. So if you have an atom, each atom will have an atomic mass unit. And that unit will have decimals. Okay? The atomic mass of an element has a numeric AMU value, however, that is equal to the numeric value of molar mass, which is gram per mole of an element. The values may be used interchangeably, but be aware that the units carry different significance. AMU is atomic mass unit. Gram per mole is exactly what it says, the gram per mole. The atomic mass unit of an element is calculated based on the weighted average of all the natural occurring isotopes, and we will show you some examples of how that's done. Essentially, elements have different isotopes, meaning they have different neutron counts. They may have different neutron counts for the exact same element. Carbon-6, for example, carbon, which has the atomic number 6, will have 12, 13, and 14 as a mass number, which means that it has 6, 7, and 8 neutrons in its nucleus. You will learn how to count these. The atomic mass of an element is listed below the element symbol on the periodic table. That's typically where you find it. However, in some new periodic tables, that's not the case. It could be off to the side. But generally speaking, it will look something like what's shown in this slide. You'll have the atomic number, you'll have the symbol, and you'll have the atomic mass, okay, on the periodic table. It's important to note, however, that the atomic mass of an element is not the same as its mass number. They are not the same. The mass number is an exact whole number. Okay? Keep that in mind. The mass number is either given, calculated, or looked up on a table. Okay? The atomic number, however, does not change. Note, when we talk about subatomic particles, the arrangement of the symbols tends to be different. When we talk about subatomic particles, the arrangement typically is mass number on the top, atomic number on the bottom. The atomic number will always equal the number of protons. The mass number equals protons plus neutrons. And it depends on which isotope of the element you choose. On the other hand, atomic mass unit is calculated based upon the average of all the isotopes, and it will give you a decimal number. The atomic number never changes for an element. The number of protons never change for an element. However, the atomic mass unit will be unique for an element, and it will be fixed at that value. Mass number, on the other hand, will change depending on which isotope of the element is chosen. Okay? So you might want to review those thoughts that we just shared a bit further. Okay? Now, Let's take a look at this concept of isotopes before we practice calculating an atomic mass unit. Isotopes are atoms of the same element that have different mass number. That's it. It's still hydrogen with one proton, which its atomic number is 1, whether it's hydrogen 1 over 1, 2 over 1, 3 over 1. These are the recognized forms or discovered forms of hydrogen. All right? Isotopes have the same number of protons but different number of neutrons. That's important to note. Okay? So make sure you figure out a way to hang on to that concept. That isotopes have the same number of protons but different number of neutrons. The atomic mass unit of an element, however, is the weighted average of the isotopes of the atom. And for hydrogen, the AMU is 1.0073. That is the atomic mass unit, and that does not change for the element. Each element has a unique AMU. Just by way of note, 1 AMU is the same as 1 gram per mole. When we think of these isotopes and calculating the atomic mass unit, we use a table of isotopic abundances. And we show you some of the most popular ones here. These are all natural isotopes. And what that means is that, for example, hydrogen, what we've already talked about, each of those has a different mass for the isotope. Now, hydrogen has 3, but the third one is only in trace amounts and it's not used in most general chemistry calculations. Okay, so in Gen Chem, for all intents and purposes, we only think of 2 forms of hydrogen, as you see on the table shown here. So these are the abundances. We will take these numbers and we use them to carry out calculations. So let's take a look then at how we calculate atomic mass, or how we report the atomic mass units. Okay, again, keep in mind atomic mass units, the terms are used interchangeably. The calculation for an atomic mass requires the percent abundance of each isotope and an atomic mass of each isotope of that element. Those are the values that we read from the table in this presentation, table 5.2. Okay, we'll either read from 5.2 or we put them into our app and we look them up. Calculate atomic mass of an element with 2 isotopes. We show you the example here. You can have more. You would take the mass of the first isotope, okay, which would be times percent divided by 100. Basically, you're changing that back to a decimal, and you're multiplying that fraction, that ratio, against the mass of the isotope, which you got from the table. For the second isotope, you would take its mass of that isotope from the table times its percent divided by 100. And you would sum those, and that will give you the AMU of the element, the atomic mass or atomic mass unit. Let's take, for example, sulfur. And we know that sulfur has an atomic number of 16. It means it has 16 protons. We also notice on the periodic table the report of a value for its typically called molar mass, which is its AMU. And we'll show you how that AMU, how that value on the periodic table was acquired. So we show you here. So we take a look at the abundances of sulfur. We see that there are 4. We see a sulfur with approximately 31.9 at about 94%, 32.9 at about 0.7%. We have 33.9 at about 4%, and then we have a small amount of 1 at about 35.9. So we take these and we basically do the math. This is math that we expect that general chemistry students can do. So you basically do the math and report the value, the AMU. It varies how many decimals they want in their calculations. Typically, I recommend that whichever periodic table you use, just be aware to be consistent with that periodic table. If the periodic table you use has 2 decimals, I would be okay with 2. If it has 3, then I'm okay with 3. I suggest not less than 2. So in any calculations in a lecture by me, I like to see at least 2 decimals in the AMU calculations and likewise in molar mass calculations. So that's what we see for sulfur. We can do the same thing for magnesium. So we show you 3 different isotopes of magnesium: magnesium 24, magnesium 25, magnesium 26, which means they're increasing in terms of number of neutrons. The atomic number does not change. It's 12. Therefore, the number of protons is 12. We do the math, and we show you here just slightly different use of the math. It doesn't matter which form of math you use. So we show you 2 examples here of how you can write down the math to do it. Do the math, calculate the values, and you get approximately 24.31 AMU. Now, to help the concept of AMU, atomic mass unit, make sense with mass number, we show you this example of magnesium with 3 of its isotopes. You would have magnesium 24, which is atomic number 12, therefore 12 protons. You'd have magnesium 25, means that's a higher mass number, and 26 higher mass number. And note that the number of protons do not change. They're all 12. Also, since magnesium is neutral, because it's on the periodic table as they exist are neutral, therefore the number of electrons also equals 12 because electrons are equal to protons in order for it to be neutral. The mass number, however, increased 24, 25, 26, which means that the number of neutrons increased 12, 13, and 14 because the difference between the mass number and the number of protons will give you the number of neutrons. Now, with neutral atoms, the protons equal electrons. But take care in not developing a habit of subtracting the number of electrons from the number of neutrons. That is not the proper process because the number of electrons, as you're going to find later in this same chapter, can change. Protons never change. Neutrons can change and electrons can change. Therefore, the standard for calculating atomic number involves protons plus neutrons. Therefore, to find the number of neutrons, we must use protons in our math. Okay? And that would be the expectation. Note if we calculate the mass, or if we look up on the table the AMU for each of these isotopes, we find that it's 23.99, 24.99, and 25.98. Mass of isotopes in AMU will have a decimal point, and I want to reiterate that again. Okay? That mass number is a whole number. It's an exact number. Mass of an isotope or AMU will have a decimal. And then we look at the relative abundance of these. We go back to the calculation we've already shown you, and that gives us a final AMU of for magnesium. Again, we like to remind you, AMU does not equal mass number. There are many other examples we could use. Here we just highlight some in this table. We'll not go into any detail on it, but take a look at this table for other examples of isotopic effects on AMU. Notice that you have the mass numbers in the symbols on in the second column. In the third column, we have the AMU, the mass numbers in the second column under atomic symbols is a whole number. The number of AMU, which is a weighted average, contains a decimal point. Now, when we consider states of matter and atoms and molecules, we must also consider the ionic form of atoms as well. So let's discuss ions. An ion is an atom or group of atoms that has a net positive or net negative charge. Okay? You'll want to keep that in mind. Ions have charge. That is the bottom line. They either have a plus charge or a minus charge. So if you see an element, atom, or a group of atoms with a plus or minus, it is an ion. That means it's either deficient electrons or have more electrons than its original state. Cations, ions, or ions with a positive charge. If a neutral atom loses one of its electrons, it becomes a cation. For some, that losing an electron bothers them initially, but it's important when you talk about electrons that you remember that electrons are negative. So losing a negative will increase the positive value of the species. Okay? So, for example, if you have sodium, you have 11 protons and 11 electrons in its neutral state. If sodium loses an electron, it will become positive by the number of electrons lost. In the case of sodium, that will be a 1 electron loss. Okay? And you will learn as we study more in this course how and why sodium loses 1 electron. And that is its preferred state, the sodium plus 1, because it's located in group 1 periodic table. Losing an electron moves it back to the noble gas, which is where it would like to be isoelectronic with, and therefore it loses 1 electron. You will be studying those concepts as well. So that's what happened with a positive charge. An anion, on the other hand, is an ion with a negative charge. If a neutral atom gains 1 electron, keep in mind you're gaining a negative. 1 or more electrons, it becomes an anion. So if you take chlorine, for example, which prefers to gain an electron because of its location in group 17, it prefers to undergo what's called reduction. You will learn that concept. It prefers to gain an electron from 17 to 18, and therefore it becomes a negative charge. So essentially when we consider ions, cations or anions, we look at the original neutral state of the element. We decide whether it's lost an electron or whether it's gained an electron. If it loses an electron, it becomes positive. If it gains an electron, it becomes negative. And that is a progression. Okay? Gaining and losing electrons. And keep in mind again, electrons are negative, and therefore you have to consider that mathematically when you're thinking of this concept. In general, metals would prefer to become more positive. They would prefer to lose electrons and become cations. In general, nonmetals would prefer to gain electrons. They prefer to become more negative. They will undergo reduction. Metals tend to undergo oxidation. Okay? And that means they become more positive. So they will lose an electron. Nonmetals would gain an electron or whatever number of electrons are necessary. Note that you can do the electron count if you remember to go back to the noble gas. Your goal is to either go back to the noble gas as a cation or go forward to the noble gas as an anion. So if you take a look at lithium, lithium is 1 step back from the noble gas. If you count starting at 1 and you go back, you'll end up in group 18. That's 1 back, therefore plus 1. Magnesium is plus 2 because you go back 1 to sodium, 1 more, you're back to the noble gas. That means there's a plus 2. The transition elements follow a slightly different thought process that you'll learn. in this course, or actually you'll get even more depth in it in analytical courses and some of the upper chemistry courses. In the case of the non-metals that will gain a negative charge, if you look at fluorine, if you move forward one, that's why it has a -1, because that's how it becomes noble. Oxygen, move over one space to fluorine, then one more space to the noble gas group 18, therefore it's 2 away. Nitrogen's 1, 2, 3 away from noble gases. Carbon is 1, 2, 3, 4 away from the noble gases. So when we see that, we recognize that their position on the periodic table is what drives its ability to either lose electrons or gain electrons. Group 14 through 17 prefer to gain electrons. The other metals would prefer to lose electrons. When these ions lose or gain electrons, we talk to them as being either monoatomic ions, that is, those that are simply one atom, one element, or those that are polyatomic ions, those that contain more than one atom or more than one element. Monoatomic ions result from oxidation, losing an electron, or reduction, gaining an electron of an element on the periodic table. The polyatomics contain more than one atom, and we will learn in this course how to do the math to determine their charge. Okay? There are also such things as ionic compounds. Ionic compounds consist of a combination of cations and anions. The formula for ionic compounds is usually the same as the empirical formula, which you will also learn in Gen Chem. The sum of the charges on the cations and anions in each formula unit must equal 0. The classical example is sodium chloride, salts, or ionic compounds. The salts on the periodic table form best when they're located in group 1 and group 2 with elements in group 15, 16, and 17. And particularly group 1 and group 17 make very good ionic compounds. You will hear me use the term salt and ionic compound interchangeably. So, how do these ions come together to form compounds? Ionic compounds are formed by interaction of their valence electrons. When it's a plus charge, that means it's deficient one of its electrons. When it is negative, it is above its neutral compound. When that is the case, the ions will come together by exchange of the charges to form compounds, as we show you in this diagram where the red lines are crossing. Essentially, to make an ionic compound, you simply crisscross the charges. This actually represents the orbitals that overlap, and then the most negative then takes the electrons and polarizes the interaction towards the negative side, and the positive side becomes deficient of electrons. So, we crisscross the charges and we get the compound. We can calculate whether or not this compound is neutral using the formula shown here. The positive charge X plus the negative charge Y must equal 0. Okay? So we can solve for this, and we can determine then that the X here must be a 3 and the Y must be a 2. So we can determine the structure of ionic compounds by simply crisscrossing their charges. or we can put it in the mathematical equation shown here, calculate the values of x and y, and then assign them. The calculation is based upon knowing that the overall charge of this ionic compound is 0. If there's some other charge, then we do the math. We assume that you can carry out this math. So if we check this, we find that the charge of this is 0 because magnesium has a +2. The positive side of this gives us a +6. And nitrogen has a -3. And the negative side of that gives us a -6. The sum of those two equals 0. Here we show you some more examples. Example of combining aluminum +3, which means it lost 3 electrons, with oxygen -2, which means it gained 2 electrons. We crisscross the charges for Al2O3, and we can check the math for the charge balance, +6, -6. Likewise, we combine calcium, bromine. We can crisscross the charges. Bromine has a -1. Calcium has a +2. We don't write the 1s in chemistry. Therefore, we have CaBr2. We check the charge balance, +2 and -2. We can also do sodium carbonate by the same process, crisscross the charges, and we recall we don't write 1s since carbonate is a polyatomic. It has 1, and we don't need brackets to contain it. Sodium has 2. Okay, now let's talk about the system for chemical nomenclature. Now, in chemical nomenclature, the IUPAC nomenclature, with its IUPAC nomenclature of inorganic chemistry, is a systematic method of naming inorganic chemical compounds as recommended by the International Union of Pure and Applied Chemistry, IUPAC. Now, there are 2 large areas where this nomenclature applies: inorganic and organic. Inorganic is the area where we look at general chemistry. Within the inorganic general chemistry area, ionic nomenclature, transition metal nomenclature, which involves D group ionic compounds, and we look at molecular or covalent compounds. In general chemistry, we don't get into the organic area other than as an overview. So how do we name these compounds? Naming compounds is a matter of memorizing the rules. There are rules, and these are the rules. These are the established rules, and the expectation that you will simply memorize them and you will follow them. So we won't spend a lot of time talking about these rules. We're going to walk you through them, and the expectation is that you'll simply memorize them and practice them. Ionic compounds have the metal plus a non-metal. Name the cationic first, name the anionic, and add IDE to the end of the name. So you have beryllium chloride. That's it. That's straightforward. Nothing more to it. Do not tell how many when it's an ionic compound. You simply name it with IDE. Potassium oxides, potassium and oxygen. Magnesium hydroxide, potassium nitrate. That is how you name it. Name the first part, second part, IDE. It is that straightforward. When you're naming monoatomic anions, be sure again that you add the IDE. We show you those examples here, or at least some examples here of how to do those. So the key is, if it's a negative part, you add IDE to the end of the name. That's it. When you name transition metals require you to know what the charge is on the metal. Otherwise, it's named exactly like any other ionic compound. First part is named, the last part is named with IDE, and in the middle of the two names you add a Roman numeral to tell what the charge is on the metal. We show you an example here with iron 2 chloride. The charge on iron is a +2. We know this is a +2, and you will learn this more and more as we practice it in this course. We know this because we have a chlorine with a 2 at the bottom. That 2 was shared from iron. Follow? In a similar fashion, take a look at iron 3 chloride. The 3 on the end of chlorine was shared from iron. In the case of chromium, chromium is a chromium 3 sulfide because the 3 was shared from the chromium. You do not have to tell the charge on the anion portion, on the negative portion. You only tell the charge on the cationic portion of it. So you do well to practice this concept. So that's how you name ionic compounds. You name the first part, followed by the second part with IDE. When it's a transition cation, you tell the charge on that cation, then tell the anionic portion followed by IDE. Roman numeral is placed in the middle. That is the nomenclature convention. Let's look a bit further at iron 2 chloride, iron 3 chloride, and chromium 3 sulfide to show you exactly how we derive the values. Okay? Now, as already discussed, the determination of the charges starts with a known value, a standard value. In the case of iron 2 chloride, that standard is chlorine. Iron 3 chloride, chlorine is the standard. And chromium 3 sulfide, sulfur is the standard. So, take a look at the math we show you here on this slide. In the case of iron 2 chloride, we start with chlorine, which has a -1 as its standard. 2 units times -1 gives us a -2. Therefore, iron must be a +2. Moving to iron 3 chloride, chlorine again is a standard at -1. 3 units times the -1 gives us -3. Therefore, for electronic neutrality, the iron must be +3. So again, this is the process we use to determine the charge on the iron, and then we assign a Roman numeral to that charge. In the case of chromium, we start with sulfur, which is a -2, times 3 units gives us a -6. Therefore, for electronic neutrality, the chromium must be a +3. We show you on this slide some more examples. We show you iron 3 sulfide. You take a look at the math for iron 3 sulfide. Sulfur is -2. 3 units of sulfur times -2 gives a -6. Therefore, iron must be a +3. Assign a Roman numeral 3. We have copper 2 selenide. We note the math for it. The selenium is a -2. 1 unit -2. Therefore, 1 unit of copper must be +2. We look at gallium 3 nitride. Nitrogen's the standard at -3. Therefore, 1 unit of gallium for electronic neutrality must be +3. We have chromium 3 chloride. Chloride's a -1. 3 units gives us a -3 charge. Therefore, chromium must be a +3. Assign Roman numeral 3. And we look at titanium sulfate. Sulfates are polyatomic with a charge of -2 as the standard. Therefore, titanium is a +3 so that we can have electronic neutrality. The key is to remember that D group transition metals have variable charge. Therefore, to calculate the charges, you want to start with something that is the standard, which means it's going to be located in group 14 through 17, or some combination of 14 through 17, and occasionally it will be located in group 13 as well, or it will be a polyatomic. So in general, you might say 13 through 17 and polyatomics. Molecular compounds are compounds that contain two or more nonmetals that form a covalent bond, which means they are both located on the right side of the periodic table. You'll learn more about this when we study the periodic table in detail. When we consider molecular compounds, valence electrons are shared by the nonmetal atoms in a covalent bond to achieve stability. They are evenly shared. Unlike an ionic compound, the electrons are not evenly shared. In an ionic compound, the negative element will have a closer association with the electrons than will the cationic element. That is a basic principle that you want to make sure you know. So let me repeat it. In an ionic compound, the anionic element will have a closer association of the electrons with it. The positive side will not have that. It will essentially be polarized, where the highest electron density will be on the negative element. And it will be completely ionic, which means it has the ability to dissociate. However, in the case of a molecular compound, it is completely covalent, meaning it's sharing of the electrons. Even though the electrons may be polarized, which you will learn, there is more of a sharing in a covalent compound than there is in an ionic compound. And so covalent compounds, molecular compounds to be clear, share electrons in a covalent bond. That is how they establish their stability, by sharing the electrons in a covalent bond. And that is important to remember. And we show you diagrams here where you get to see what's called the Lewis dots, and we'll show you how to do those in this course. They come together using the valence electrons, which you will learn more about. We're introducing the concept here. When they come together in a covalent bond, covalent bonds share the electrons. When they come together in an ionic bond, they don't share the electrons. The electrons basically transfer from the positive to the negative in that structure. So how do we name these compounds? How do we name these molecular compounds? Let me show that to you by using an example. Step 1. Name the first metal of the element with its name, by its name. For example, in the case of NCl3, the first name is nitrogen. Then, name the second nonmetal by using the first syllable of the element's name followed by "ide." In other words, you're going to put IDE again on them. Got it? So that's the other part. So you're going to have, in this case, chloride. So we know we at least have nitrogen chloride. Then you must add a prefix to indicate the number of atoms for each of these species. Okay? Because there is one nitrogen atom, no prefix is needed. When there's only one atom of the first element, do not use mono. Okay? Do not use mono for the first atom when there's only one. Because there's one atom of nitrogen, no prefix is needed. The suffix 3 on the chloride, on the other hand, is written with the prefix tri, and you must learn these terms. Tri means 3. Therefore, the name of NCl3 is nitrogen trichloride. That's how we do it. Those are the rules for naming them. So you must memorize the rules. You have to practice them. You get used to them. There's no magic to this. There's no deep thought to give to it. It's like memorizing names of relatives. So let's repeat these rules. In a molecular compound, prefixes are used to indicate the number of nonmetals. Okay? Whatever that is. So you have to use prefixes. Prefix mono is not used for the first nonmetal in the compound. So, for example, NO2, and I'm saying that on purpose, NO2 is nitrogen dioxide. It is di because there are two oxygens, there's only one nitrogen, and we don't say mono. When the vowels O and O or A and O appear together, the first vowel is omitted. That's the system for naming them. So this would be carbon monoxide. It is monoxide because it is one oxygen. We do not tell that we have monocarbon. We only tell if we have mono of the second nonmetal, because molecular compounds, covalent compounds, are formed from nonmetals. This table shows you the prefixes that you are expected to know, and you'll have to simply learn them. 1 mono, 2 di, tri, tetra, penta, etc. Many people tend to just know these by now. It's kind of one of those things that over time you've somewhere learned, so you will be using them. Here's some more examples. Hydrogen iodide. We don't call it, by the way, monoiodide. And there are a few anomalies in all of the nomenclature. You have nitrogen trifluoride, sulfur dioxide, dinitrogen tetrachloride, nitrogen dioxide, and dinitrogen monoxide. So you will want to take a look at these and you will want to practice them. This shows you some other examples of some common molecular compounds. Take a look at them to help practice through it, including showing you some hydrates. You will want to take a look at how to name these hydrates as well. And speaking of hydrates, here's some example. Hydrates are common compounds that have a specific number of water molecules attached to them. So you have to tell how many water molecules. So you name the first part of the compound as you would. In this case, you notice that there are salts. That is typically where we see these hydrates as salts, okay, as ionic compounds. Again, I tend to use salts and ionic compounds interchangeably. So here's an example. You'll have barium chloride dihydrate, 2 water molecules. Lithium chloride monohydrate, 1 molecule. Magnesium sulfate heptahydrate, 7 water molecules. And strontium nitrate tetrahydrate. And you also see the copper sulfate pentahydrate. So the difference is with the water, we see a difference in color, and that's actually why this is used as what's called as a drying agent, a color indicator drying agent. You'll put it in a drying tube because when it absorbs water, it tells you it's there because it turns blue. So it's used as a water indicator in many laboratories. Let's finish this lecture with a really broad stroke overview of acids. The expectation is that you will actually simply memorize many of these acids. So what are acids? An acid can be defined as a substance that yields hydrogen ions, H+, when dissolved in water. In the case of HCl, for example, we dissolve it in water and we produce what's called a hydronium ion plus chloride ion. This table shows you many of the other acids of this type. Again, the expectation that you can look at these and memorize these on your own. One of the characteristics of an acid is that its pH is less than 7. That pH is calculated by using the equation pH equals minus the log of hydrogen ion concentration. We also note that 1 times 10 to the 14, which is this Kw, equals the concentration of H plus times hydroxide. For Gen Chem 1 at SVSU, this is the extent of your exposure to pH and being able to calculate pH. What about bases? A base can be defined as a substance that yields hydroxide ion when dissolved in water. And we show you some common bases here. Characteristic of base is pH is greater than 7. We can calculate also the pH of a solution of a base by simply converting the hydrogen ion concentration to the hydroxide concentration, or vice versa, and calculating using the pH equation minus a log of H plus, or for bases we can use POH, calculate a POH, and subtract it from 14 to obtain the pH. There are other acids that we could talk about, for example, the nitric acid, carbonic acid, phosphoric acid. These are the oxal acids. Is an acid that contains a hydrogen, oxygen, and another element. And these are acids that we expect that you can look at and memorize. And we show you here how the oxal acids are named, the rules for them. When all the H atoms are removed from the acid, the anion is named 8. So when there are no hydrogens, okay, the anion name is 8. And you can see the other rules here as well on your own. The IOUS, the anions are named ITE. And so this is a matter of looking at the rules, memorizing them, which again, the expectation is something that you can do all your own. Simply memorize the rules and follow them. Show you some examples of dihydrogen phosphate. We show you hydrogen phosphate, and then we have phosphate itself. So that concludes Lecture 2 of Chapter 2, SVSU Chem 111.